Yeah, I'll check with the dean whether I'm well within my rights to have this kind of 15%. I've done that in some of my courses in the past, and I've not got any objection. But if you guys have any objection, I will send out an email. Okay, you have to let me know, and also do the thing. Okay. Yeah. So being open by. Okay, so Anli, I have, prompted by your very, legitimate question about reading material. I sent a couple of mails. I have uploaded links to where you can find, okay, two textbooks that I could do. I don't know if you guys have bothered to read the email or not. Okay, so I've sent it. I've sent that information, so I'm announcing it today. So you could go read that email, okay, at your leisure. And I will, I've already given some references to which chapters are relevant for what topic. And I will make that, I'll try to put that in a spreadsheet, and I'll send it to you as well, and I'll upload it. And if you care, you can read them, okay, and do whatever you want. Okay.
Hello,
so
sir?
Yes.
Yeah, so this decision procedures books link is asking me that it's not giving me permission. It says you need access. And
Which one?
This is the decision procedure link, the Google Drive link, I think.
I see. What does it say? It says no permission, is it?
Yeah, it says you need access, and it's like there's a button for request access and such. I'll do the request access, I guess.
Yeah, but I did not get any request access. Did you try it again?
Yeah, I'll try it again. This will go, I think, to your Gmail email account.
It is my Gmail account.
Yeah, it says request sent.
Oh, I see. So I'll look into it. Okay, and I'll fix it.
Yeah, sure.
Yeah. So last time we looked at, in detail about how SSAs are generated for loop unwindings. Okay, and I showed you, two ways, in two ways that it could be generated. Okay, and the one that one way was to really represent the loop unwindings as nested if then else. Okay, and you have one assertion check for every time you get out, you exit the loop after for each of the iterations for however many loop unwinding that you have. But that, of course, that will mean that you will have to generate one VC for every assertion. But then I showed you that there is a better way to generate one assertion for all the unwindings. Okay, and that is how for this particular loop, you could after 0 iteration, this an SSA which corresponds to the this piece of code can be used, or if you have k is equal to 1. So the idea here is not to insert an assertion after every else's, but you just merge all the nested if then else's. But if you merge all the nested if then else's for the unwinding, but then you have to make sure that you only get out after after each of those iterations. And when you merge and then you have a single assertion, you will also end up getting to the point of the assertion in more than by just getting out of the loop. For example, here, if you, for k is equal to 2, if you had two unwindings, so there will be two copies of your body. And then if you just have, else and else with empty statements, there are three ways of getting, reaching this assertion. One is after each of the, after a zero iteration, okay, when you get out even without entering the loop. Or if you can get out after entering the loop once, and then making this this condition fails. Now, but if I merged it like this and then I put the assertion, then you will end up reaching that even in the situation where you would have done to the incomplete, okay, because this only this code represents only for two iterations. There is an additional way inside these through these if nested if that you can get. But then since we wanted the check of this assert to happen only for each of the iterations up to the unwinding depth, so the trick that we use is you force an assumption here saying that I need to check this assertion only after exit in the first two cases. Either I don't enter the loop at all for k is equal to 2, the two exit points are this being violated or the other one being violated, and that's the assumption that that I'm making here. And if you compare, when you do the assignment and you compare, I'm asking you to compare the SSA generated by CBMC for loop unwindings as well as these an equivalent code that I have proposed here, and that is the purpose of problem 2. And you can check that the SSA generated by CBMC exactly corresponds to representing the unwindings in this fashion. So and you've spent quite a bit of time on the SSA generation. So I'll take and I've also emailed a reference, a reading material, a reference to a reading material that discusses this in SSA. And so you can, unless you have any questions right now, you can consult that reference. Any questions now here between the two of you?
No, sir.
Okay. So let me now start with this. So the question is, now the question that one can raise is, okay, we have seen how to do a bounded analysis of software through unwindings, through loop unwindings. And we already discussed how one can do unbounded analysis, that is analysis of a program with loop for arbitrary unwindings through the use of inductive invariance or loop invariance by actually proposing a condition, a loop invariant condition, and that satisfied a few properties that we discussed. Once we have that, then the whole logic itself suggested, using the inference rule for the whole logic, you could decompose the proof of the verification of an unbounded verification, and the verification of the behavior of the program for all unwindings through these three checks on programs that do not have loops. And the initiation check, which checks that when you enter the loop invariant point, the point at which you associate the loop invariant. The first time the loop invariant holds, that's the initiation check. The inductiveness check checks that the proposed predicate is indeed inductive, by checking if you assume it prior to if you start with the state in which the loop invariant is true and you execute the body of the loop, the loop invariant. If you start with the state in which the loop invariant holds and you execute the body, which is possible only when the loop entry condition is true. And that goes to assumption. If you execute the body, then the loop invariant holds good again. This can be stated also as if you start with a condition in which the loop invariant holds good, and then this checking of this condition can also be done by means instead of the body. The body can be conditioned using an if then thing, and then you have to do an exit check. Okay, that
I wanted to ask this last time. Shouldn't exit check be I equal to 10?
No. Should this be I not equal to 10?
No,
but that's the loop. That's the loop condition. No, that's the loop condition is I not equal to 10. Correct? Yes,
that's for induction. But when it exits, the loop condition should become false, right?
Yeah, but this inductive. Okay. There's a mistake in the exit check. You're right. So in the exit check, it should be the negation of I not equal to 10. You're right. That's a good thing that you noticed. Yes. Okay. Yeah. So I guess the point is this has to be a negation. So which means that it has to be I is equal to 10 because that's the condition in which exit loop. Good. So how can this is how you would do if you were doing Hoare proof. Now the question that I'm raising is, can this way of analysis, if you proposed a loop invariant, if you could do that using, let's see, so someone dropped off. Okay. If you could do with CBMC, the same flow of decomposing into 3 different checks can be implemented, or if you could instrument that within CBMC. So that's what I'm going to show you. Okay, and this is quite interesting. And this is with the use of. So how can you do this method of unbounded analysis that I've shown you with a proposed loop invariant? And here, I'm using the feature of non-deterministic assignment and the feature of making assumptions in selected way to do that. Okay, so consider this, this code. Okay, this is for the program that I've, for this program that I've shown you here on the right side. Okay. So, so this is the initialization part of the code. So in order to do the initiation check, I can put an assert here, correct? Okay. So here I'm, the loop invariant that I'm using is that X is even and I is less than or equal to 10. Okay. So you can do the initiation check by just putting in this one. And then the exit check, okay. The exit check is where I'm using the trick. So here I'm replacing for the exit check. Okay, for the So the idea there is to replace the body of the loop itself by a non-deterministic assignment to the variables that are modified in the body of the program in such a way that they could take any value satisfied by the loop invariant, because that's what happens, right? So if you, what happens in the loop, and that's what I'm doing here. As you can see, I am assigning to X and I. First, I assign X some non-deterministic value. When I do this non-det uent, X takes an arbitrary value. After that, I constrain it using assume as per the in such a way that the value is constrained to be anything, something that satisfies the loop invariant. So in this case, X has to be even, and I has to be less than or equal to 10, and that's what I'm doing with these two things. Okay, and then so that way, as if I is equal to if I is not equal to 10, then I execute the body. Okay, so the execution of the body over all iterations is what is constrained to be such that it satisfies the loop invariant. After all, the loop invariant here is being used in a way to abstract the effect of executing the loop for as many iterations as it would get executed. Okay, that's what the loop invariant characterizes, and that's what I'm doing here. Okay, and then after that, I force through an assume statement the condition that has to hold good when I exit the loop. Okay, as long as I enter the loop, I can arbitrarily assign some value that is consistent with the loop invariant. That's what this thing is doing. And I force an exit when I do reach the assertion. This is the exit point for the loop. So we know that that point can be reached only when the negation of the entry condition for the loop is true. And that's what I'm forcing it by an assumption. And then I will check the whatever is the post. Okay, so in this case, I'm sorry, I mean the post is actually just this. It's X, it's even of X, so it will be just even of X. Okay, whatever is the post conditions, and that's what you will do. Okay, so this will take care of the kind of you're replacing. You are doing that. Assuming given this is a loop invariant, then you can pretty much, so by doing this is a very clever way of getting around having to unwind, okay, and using the loop invariant as a crutch. So now you could do this for a program with arbitrary number of loops. All you have to do is for every loop, if you can propose a loop invariant that is a safe loop invariant, a loop invariant that would satisfy these three conditions, okay, then you could pretty much replace every loop by this trick, by some set of statements that where you force the variables to take any one of those values that are done by the that is consistent with the loop invariant, then you check. So so this way you could do a unbounded, this has the effect of doing an unbounded analysis. Okay, of course you have to you have the responsibility to check that this loop invariant, which was the basis for you to be replacing this loop with respect, that indeed your body, the actual body of the loop satisfies this inductiveness check, and that can be done separately by this one here, by running CBMC to check this piece of code. So you assume that This is exactly, so you're assuming the loop invariant to be true at the beginning. And then if you enter the loop and execute the body once, starting with an arbitrary state in which the loop invariant holds good, and that's what this assume does, then after executing it, my loop invariant holds good. Okay, so this is the inductiveness check. Okay, assuming that you have done the inductiveness check, that is the check to say that this indeed the proposed loop invariant is inductive. What this piece of thing is doing is you are using that loop invariant to replace the loop. Then you can do the check, okay, for the whole thing. Yeah. So this is how you could use the bounded analysis method by splitting the problem into this way. Okay. So do you understand this? Any questions here? Yes, no?
No.
Okay. So are you convinced that why? So let me ask you the questions. Why is it okay for me to replace the loop with this code? I just now explained it, but I just asking. What are the possible values that X and I can take by this one?
So they will be non-deterministic?
Yeah, non-deterministically, it can be any value that satisfies the loop invariant. And the loop invariant that I'm using is it's even. So as long as I'm inside the loop, okay, which is what this thing is, forcing it. So I have, I make sure that whatever the value of X is even, what I'm abstracting. So in that sense, this way of doing it is usually called abstraction of the loop. Whenever you do abstraction, you're throwing away the details. What are the details that you're throwing away? I'm throwing away exact, the sequence in which the value of X changes, okay? X and I change. Rather, what I'm capturing is, as long as I'm inside the loop, it is capturing all the possible values that X and I can take. Correct? Okay, and that's what a loop invariant is supposed to do. In this case, I'm using the loop invariant that even if X and I less than or equal to 2. So I'm throwing away some, certainly a lot of details. And also this is sometimes what is called, it's an over approximation of the loop, in the sense, you see that it includes, just the values that it can take, include not only the actual values. For example, it can be I'm allowing X to take any even number, okay? And of course, I know, can only be less than or equal to 10 as long as I'm inside the loop, because I'm starting with I is equal to 0. But for X, not only it is, including, this one is not exactly equivalent to this loop, in the sense that it allows values to X that in actuality X may not take, okay, because it allows other even numbers as well, which for example, something that's greater than 20, okay, but it doesn't matter, okay, for this particular assertion that loop invariant is good enough, okay, and that's why what I've shown here, this program here, which replaces the actual loop with a set of statements that constrains the value of X and I to be some arbitrary value that satisfies the loop invariant, you are, since a loop invariant itself only certainly includes the actual values that X and I take during all iterations, but it can also include values that it may not take. But that is okay because that loop invariant, as we said, is strong enough is something that is inductive, that is indeed includes all the values that it can take, and it is strong enough along with the exit condition to prove my post condition, which in this case is even of X. And that's why, so although these are not equivalent, but there is one very important property that this program on the left side satisfies. That is, this program is an over approximation of the loop in the sense that it make sure that all the values that that X and I can take are included, but possibly more things. But and it is such that when I exit this condition also. Therefore, if this verification succeeds, the verification of the code as I've defined here succeeds, then I can be sure that with this loop invariant, my post condition has been verified. So pretty much what I'm doing is I'm using CBMC to simulate these three checks. Okay, so this program here, this abstract program, does the initiation and exit check. Okay. Whereas this one takes care of the inductiveness check. So this is something that can be done with CBMC also, and then extend CBMC's power to doing unbounded analysis. Okay. Okay. So let me move on now.
It feels like this would have been better if we could somehow give the inductive invariant as this sort of annotation instead of replacing the code. Are there software for that?
No. See, if you did only as an annotation, okay. Now, yeah. I mean, what you say is, okay, I'll give this as an annotation here, like I've done on the right side, okay? And then internally, it can do all these things, right? Okay. So now I manually, of course, there is always this manual content to this of the cleverness that the human being has to add, the act of proposing the loop invariant, okay? So now I think what you're asking, if I understand you correctly, is why not, the CBMC do automatically, okay, these two things that I did, okay? So all, if I just put this as an annotation, why not? It does all this bookkeeping details, which I showed here. Yes, it could be done, but CBMC is intended, as its name indicates, as a bounded model checker. Okay, and that's why it does not support this as nicely as the thing. Now, there are, for example, proof checkers. See, this business of decomposing into these three things is actually justified by OR logic. Okay, so there are semi-automatic mechanized implementation of OR logic, which they support this. Yes, you could have a feature maybe of CBMC where you are required only to give the loop invariant as an annotation, and it can internally under the hood set up this. Do this, what I've actually manually done. Yes, that could be done. Okay, and you could actually instrument those kinds of things inside CBMC. Okay, there might even be a tool to do that. CBMC, I mean, this is just something that I'm saying, but CBMC itself does not do it because there could be so many other things that one could be asking for. So CBMC is basically a bounded model checking tool for C. okay? But it does provide you with this nice features of making constrained non-deterministic assignment. That's what I call this, okay? This two put together is what I call as constrained non-deterministic assignment, okay? Because I'm assigning non-deterministically assigning to X some value that is constrained by this condition. Okay, so what CBMC provides, by the way, under the hood several hooks, okay, that allows you to instrument CBMC, and you can do kind of build extensions to CBMC to automate this thing. Okay. This would be, so you could use these hooks that CBMC provides. You have to go one step under the hood of CBMC, okay? And then you have to add a few things, use those APIs to these, what I call as hooks, and you could extract what Chandradeep that you called as annotations, and then automatically set up these two things and then say verified. Okay, it could be done. It's just that CBMC just provides the hook and then it leaves that to other more people who want to build specialized tools. Yeah, but that's a good point that you observed. So why can't? Did that answer your question? Huh?
Yes, thank you.
Yeah. Okay. Okay, so the next topic that I want to move into is to, now, okay, Chandradeep brought up already, okay, if assuming I propose loop invariant, how about automating those checking of these three things, okay? Now, a step next to that is, why not have a loop invariant automatically generated? Now, that's a very hard task, okay? Generation of loop invariant is a very challenging task. It's even an undecidable one. But yet, you could probably have methods generate, and that's what I'm getting into, okay? Right now. Now, there is very rich theory behind this, what these loop invariants are. We've already seen there are multiple candidates for every loop. There are multiple possible candidates that can be used as a loop invariant. And there are some strongest one and the weakest one. How do you generate these things? And what are exactly this as a formal object? In order to that's the thing that I'm getting into. So next couple of lectures, we will just give, develop the theory of what are called fixed points. And we see that every fixed points for a loop, and every fixed point happens to denote a loop invariant, a predicate that can possibly serve as a loop invariant. But in order to do this, that theory itself doesn't work at the code level, but in terms of C code, but it does in terms of programs being represented as transition system. And therefore I'm going to show this what it means for a predicate to be inductive. Okay, what it means for a predicate to be inductive in a transition system formalism. Okay, so first I draw your attention to the left side. Okay, so as you know, what exactly here, this is the Hoare inference rule for while. Okay, all it says is if P is a loop invariant, okay, and that's what the assumption is saying about the line, then if I then I can conclude that the conclusion under the line for the so that is the basis for replacing the entire loop with the loop invariant, okay, which is what I used for checking, for doing the check there without loop. So what was it saying? So this is another way to represent this is P is such that if I start from any state in which P is true, and then I execute this thing, if this statement, if B then Q, okay, then I'll I'll be in P will hold good also in the post state. With these two things, you can see that if this is true, if I start with an arbitrary P state and I execute this command, then you can keep extending this, okay? Because by using the sequential OR logic, then I can also conclude that if I start with P and I do 2 iterations with the body, then P will continue to hold, because I can use this to push P to after the first one, after the first iteration, and so on, okay? Now, the same thing can be did. We have seen that these code, for every piece of code, you can also represent the effect of executing a piece of code by means of a transition relation, which relates S and S prime. This is one formalism of representing it as a code triple. Now, the transition system is one model in which you directly represent the effect of executing that code as a formula, first order formula relating the state S, any state in a pre-state, to a post-state, which is denoted by S prime. So okay, okay, by the way, and another point, I keep saying being inductiveness, the inductiveness attribute is a property of a predicate, okay? Usually you say P is inductive or P is not inductive, okay? But it is usually the inductiveness property, it's a property of the predicate, but it is relative to a loop, relative to some body or some loop. In this case, specifically the body, but it is the body. So when you say, is P inductive? Okay, obviously that question does not make sense. It makes sense only when you associate that predicate with respect to a loop. So you should bear in mind when I say P is inductive, it is usually with respect to a particular loop, and that is and in particularly the loop body. Okay, so it says something about what that P is preserved over by the loop body. Okay, that is, it is preserved. So no matter how many times, as long as you keep executing this statement, if B then Q, then P is preserved, and that's what the loop invariant satisfies. And that's when you say that a predicate P is inductive with respect to that body, which forms the that piece of code, which forms the execution of an arbitrary iteration in the loop. Now, if I model the same program as a transition relation, like I've shown on the right side, then P being inductive can be checked by this formula. That is, if I start with a state in which P holds, and I do one step, I do one step off the code representing the execution of the body, that is, T corresponds to if B then Q, then whatever the state that I get, post state, will continue to satisfy P. Okay, that is kind of pictorially, I'm showing it here in this picture. Suppose P, which is a predicate, which could be any predicate, I have not defined it, it can in general be defined as a formula, first order formula, which you will also see. Suppose that has all these states, these small circle states, okay, in P. So this set denotes the set of all states, okay, that satisfies P. And of course, T here is the transition relation. So that defines the next state, okay, after executing the body. So that's what I've shown here, okay. So in this particular state, after executing, it goes back to itself. So here you may go to something else, and then you're going back in here. But see, you look, all these things are, maybe the different ways in which, you get among the states that result as a result of executing the body, which in this case represented by T, one or more times, okay? And P being inductive requires that no matter how many times you execute the T, you're back, you will always get, it will result in a state in which P is true, okay? So that's what this is checking. So in a transition system formalism, okay, if you want the inductiveness check for of a predicate can be expressed in this fashion, and this is what this thing means. More specifically, if I compute the image of P, the states of P under this transition relation T, then that image itself will be inside P. And that's what this thing is saying, okay? Viewed as sets of states, okay? This is what this thing is saying. If P predicate is inductive relative to a transition relation T, if this condition is satisfied, and that actually means this. So you see, and here I'm representing, if you view them as predicate formulas, then something being a subset in terms of, as when represented as sets, really is equivalent to saying that it is image of P implies P. That is, if image of P, I represent the image as a formula, okay? That means that that should imply P. Now, this should automatically suggest to you a way of generating one inductive invariant, one way of generating an inductive invariant for when you express the body as a transition system. How? You could keep on, okay? The strongest inductive invariant, as I've told you earlier, is inductive invariant is a predicate that is represented by a formula which characterizes precisely the set of values that the set of states that it can ever be reachable in any of the iterations. Okay, so one way of doing that is I start with, and that must certainly include the initial. So you start with the initial set of states, and then you keep on adding these images. Okay, you compute the images, and then you keep on adding it. Okay, and then when you reach a point where you when new images that you add will not change the current set, then you know that you have reached a point where the predicate that you have, okay, which is obtained by incrementally adding images of 1 step, 2 step, 3 step, and so on, until you have accumulated all of them, at which point that predicate, which denotes the set of all accumulated states, will be inductive. Okay, and that is what that notion of when you reach this saturation point is what is that notion is called, you've reached a fixed point. Okay, and that can be formalized as a property of a function, and that's I'm leading to that, and that requires you to understand get really acquainted with representing formulas as states, and kind of a peek into the higher order function and so on, because the notion of fixed point will be defined over particular kind of structures, which are lattices, and higher order function which map predicate to predicate. Okay, in the thing. So my the purpose of the third problem in the assignment is to get you comfortable with the nuts and bolts that are required for you to understand inductive invariance as fixed points of certain higher order functions. Okay, so now I'm going to kind of ask you a few. I'm going to review the third problem in the assignment, and if you've attended this class, I will give you I will help you get answers to that question. So you have the advantage of being able to answer that question when you do the assignment. Okay. So here is a piece of program. Okay. Which there are two Boolean variables. Okay. So it is meant to manipulate a bit vector of size 2, okay? And each bit I'm representing by a separate variable. But my state is a bit vector, a pair of bit vectors, x0 and x1. What is this doing? It is just rotating, okay? It is rotating the that bit vector, the bits in the bit vector to the right with the wraparound, okay? And that's what the rotate function is supposed to do, okay? So it is, rotating and then assigning it back to the thing. And then I keep doing it. This is actually a non-terminating program. I have a version for it, a terminating version also, but I'm deliberately here to show you, make you prove a point, and I'm just making the thing. And then this thing is what is the strongest inductive invariant, and I'm going to by converting into a transition system as a transition relation, I'm going to illustrate that point. And then starting with next class, I'm going to develop the theory of fixed points. Okay. So if you want to model this as a transition system, a transition system where you model a transition relation where the effect of executing the loop can be modeled as repeated cumulative execution of composition of these transition relations. So you can do that by characterizing by the initial condition prior to entering the loop as the initial condition of the transition system. And I model the body of executing the arbitrary execution of a single iteration of this loop as my transition relation. Okay, that's what I'm doing. Okay, so prior to entering the a particular iteration, if my state is my bit vector is x1 x0, then this TS predicate, binary predicate, defines the post thing, which models the effect of rotation, and that's exactly what I've modeled here. Okay, so if the state that I get after executing the primed variables, then what should that be? The rotation means it could be the x1 prime should be x0, right? Because I assume that there is a wraparound, and x0 prime should be what x1 was. Okay, so that is capturing the effect of rotating a bit vector by one step, which is what the body of the loop is doing. Okay, is that clear? So are you convinced that this relation represents the effect of executing the body of the loop? Yes? No? Any
Yes.
doubt? Okay. Generally, if there is see, in this case, the loop entry condition is true. Okay. If it is something other than true, then you will have to your transition relation will have to include that. Okay, it should be over the code, which says if that condition is true, then I execute the body. Okay, because here the condition is true, so that doesn't add anything. Then I want to first introduce you to this thing. So what does I am, this represented by this formula, denote? That is the first question in that assignment. There are only two of you here. Okay? So let me ask you that. Any one of you, what do you think this is? I mean, we've kind of gone through what exactly existential formulas that use existential quantification, what they represent as set of states. Okay. So whenever I ask you this question, and this is for, yes, tell me, Chandradeep.
So y0, y1?
Yes.
Y0, y1 such that y0 or y1 equals 1.
No. Why? Why do you say that?
Reverse the t and then applied the init.
Okay, first of all, image is represents a set of bit vectors. Are you convinced? Okay, because there's, T is a binary relation, TS is a binary relation, but this one is eliminating one of the variables. So it is saying, so it asks the question, what are some of the values for which, values, y1, y0 values for which this could be true? Okay. It is true. Is it true for 1, 1? Okay, maybe that's what you were trying to answer. Okay, let's start with thing. Is it true for 0, 0? How will you answer that question? You have to plug in 0, 0. Okay, if I plug in 0, 0, it is true if what? If there exists an x1, x0 such that init of x1, x0 is true, and here T, I'm sorry, there's a syntax error. T should be TS, such that there exists a bit vector such that x1, x0 that gets mapped by this transition relation into y1, y0. Now TS is a result of it. So your question is, does if y1, y0 is 0, 0, is there an x1, x0 that you start with after rotation, it will end up being 0, 0?
Yes, 0, 0 itself.
Yeah, 0, 0 itself. Therefore, certainly IM is true for 0, 0. Similarly, is it true for 1?
Init of 0, 0 won't be true, right?
Huh?
Init of 0, 0 won't be true.
Yeah, I'm sorry. So, yes, you're right. I'm sorry. That's a good point. So init of 0. So it does not include 0, 0. Okay. So it does not include 0, 0. But how about 0, 0, 1? Yeah, you're exactly right. I made a mistake there. So 0, 0, it does not, because this will be false. Okay. Init itself will be false, and you can never find an x0. It doesn't matter whether the second one is t is true or not, because it's false. And therefore, it certainly, for y1, 0, 0, it is false, because init itself is false. Good point. Okay. But for 1, 0, 0, 1, and 1, 1, it is true. Why? Because if you say for 1, 1, it is indeed, 1, 1 satisfies init. Okay. Because init says x1 or x1, and 1, as you said, 1, 1, when you rotate, 1, 1 remains 1, 1, and therefore this is true. And similarly, 0, 1, 1, 0, which are also in init, for both of them, there is a pre-value that when rotated, will give you that value that you're looking for. So if it is y1, y0 is 1, 0, then your y1, y0 is 0, 1 bit vector, then there is the other pre-value is 1, 0. Okay, and that's why this one exactly represents the image. Okay, so which I have denoted here pictorially. This is the one. This is exactly what this represents. So if your init is all these values in this circle that I'm showing in the cursor, what I am really represents is the image of that set under the transition relation T, the result of applying the transition relation to all the states. Okay, and that is the image. Okay, so you can see this is what I call as a symbolic representation of image. Okay, under a transition relation. Bingo. So you see, so you could represent that set now using existential quantification. Okay. Now let me move to the second one now. So is this clear? And Leap, this is very important for you to understand, because before I move to fixed point theories, you'll have to be very, very comfortable with understanding this correspondence between formulas using existential, predicate formulas, first order predicate formulas, and the set of states when viewed as a predicate over the variables it denotes. Extremely important. If you want to succeed in this course, you will have to become adept at viewing that. That's why I keep short of begging you to actually spend time in working out the examples and so on. And I'm very disappointed that people have not even bothered to listen to my thing and come ready for the class. Okay, but let alone being ready for the class, even coming to the class. Okay, but that's all I can do. So I've been doing all my best, and then the rest is up to you. So this is very important. And Lee, do you understand this? Okay.
Yes, sir. I have one confusion.
Yes.
When it's 1, 0 or 0, 1, how does the transition system work then?
Yeah. So suppose your y1, y0 represents the bit vector 1, 0. Okay.
Yes.
So what you have is, let me use this. So if I'm checking if IM is true for 1, 0, then what is this? What is this? Okay, this is equivalent to if there exists a x1, x0, okay, such that TS of correct?
Mm-hmm.
Hmm?
Yes.
Is there a x1, x0 for which TS of x1, x0, is there a first argument, x1, x0, for which TS is true, with the second argument being 1, 0?
X1, x0 will be 0, 1 that time?
Yeah, that is a 0, 1 value. Therefore, okay, does that 0, 1 satisfy init? Mm-hmm. Yes, it does. Okay? Yes, it does, because init is defined as per init. It does satisfy that. So the moment you find an x1 and x0 such that these two, init and TS, is satisfied for this particular value, the existential quantification is true. Okay?
Mm-hmm.
That's why, that answer, yeah. So your question was exactly this TS. Okay, that's why it is true for 1, 0. Okay, as long as there is some element in my tree state, okay, that gets mapped, that is in the initial value. So this is actually an image of the set of initial states under the transition relation. Okay, that's why the states that for which IM is true are exactly those states which is included, which is in the image of that is produced by applying T to the initial set. Yeah.
Yes, sir.
Okay, good. So now let me ask this. So this is done. So second question is this. Now all I've done is I've parameterized. I've defined another function, which is a higher order function, which takes a predicate and gives a predicate. Okay. And that predicate that it returns, it takes a predicate as an argument, P, and then similar to what the image. So it says there exists set P that does it exist a P, a bit vector, which is a P state, which means it satisfies P, and it is true of those things, and it is that gets mapped to y1, y0. So this one is just the first one was hard coded to compute the image of the set of initial states. Here I am parameterizing that with respect to a predicate P. So which means this one computes the image of P under T. That's what this thing does. Okay, it can so it is parameterized. Okay. Now, what does suppose I define an IM? Okay, I have not defined IM here. So, but let me show it pictorially. Let's suppose I do this. Okay, I'm actually defining IM as okay, so here so I'm actually denoting here. So I'll get to that picture, so maybe I'll have the picture here. So I'm defining IM0's IMP of false. So what does IMP of false denote? Oh, it's 3:16. I don't know. I mean, I'll take 5 more minutes. I hope you can do. Yeah. What does IMP of false denote? So if P is false, IMP is you have to plug in false in place of P. Okay. If P is false, then obviously this whole thing is false, correct? Mm-hmm. So there can never be things. So IMP of false is false. Okay. What does false denote? False as a predicate, what does it denote? Nothing can satisfy false, and therefore it denotes the empty set, correct? Yeah. So that's what this thing here in the picture. Okay. Now, suppose I denote by IM superscript 1, this one, IMP with lambda x, this function. All this is doing is, it is computing whatever, it is computing the image of whatever predicate that I got from here, that is IM0, and then to it, it is adding all the initial state. Now, IM0 of x is already false. Okay, so IMP of false, so IM0 is false, so IMP of false is false, and so for that I'm adding init, correct? And therefore that one will be, this one will be init. So it will be exactly the set of initial states. And then I will keep repeatedly applying this IMP with whatever I got from the previous thing. Okay, then I'll be doing, then I'll be getting IM2, which includes not only the initial union of the initial state and all the images, the image of init under T. Okay, that's what IM of T does. Okay, in the third step, then I'll be computing the image of this whole thing and adding init to it. Okay, and if I keep doing it, you see, then eventually it has to, if it terminates with if I reach a point when I'm not adding any more states to it, which under certain conditions is guaranteed to hold. Okay, what those conditions are is this may not terminate. Okay, that is always the case, and it may terminate. But if it, suppose in theory you reach a point at which IM applied to IM of I is included, is included in that. It is same identical. That is when we say that it reaches fixed point of you have reached a fixed point, and that is so because each of these is, what is it doing? It is adding a disjunction. Okay, so although I'm showing it in set notation here, what in the left side here, I'm exactly showing, if you expand all these things, you're getting a big formula, big fat formula with nested existential quantification. Okay, and that when it reaches the fixed point is the strongest loop in it. That will be inductive. Why? Because of this condition. Okay, because it's a closure. Okay, an inductive predicate is a closure in the sense, if you apply it once more, then you're not adding anymore. That's the concept of a closure. Okay, and fixed point is equivalent to a closure. Say so these inductive invariants are fixed points of appropriately defined. So in this case, I defined a higher order function in terms of IMP of P. Okay, and that I use to apply to itself in this fashion. So the fixed point of this appropriately defined thing is one of the inductive predicates. So how you design this higher order predicate will give you all the fixed points. Okay, it's a beautiful theory. I mean, you have all your fixed points as you have all your inductive invariants as fixed points of various image kind of computation over the starting state. I mean, usually it's the starting state that you'll have to vary. All of them will use a transition relation representing the body. Okay, and this is exactly what the fixed point is. And so we will get more into this. It's just I'm giving you a peek into it. And first we will develop the theory of fixed points. Okay, and then come back into various different methods to automate computation of this fixed points. And that's when I will get into abstract interpretation, model checking. So this is exactly a complete model checking. Okay, implementation, somewhat efficient implementation of this kind of fixed point is the naive method for model checking. Okay, I'll stop here. So you have any questions before I stop sharing?
No.
Yeah. So good. Thank you for showing up, and you will get a few emails, about the announcements that I made today, specifically 2 things, and keep a watch for that. Thank you.
Thank you, sir.